that solidification, there are two broad categories. We call it, some grades we are call it, they are sticker grades, that means tendency for sticking is the high. And as I have told you, since they are sticking towards the mold, so the heat transfer is relatively high. That means the dendrites will be relatively finer, so the grains are relatively finer. So what is the chemistry ranges? For carbon equivalent less than 0.06, carbon equivalent has to be less than that, or it has to be more than 0.2. In these chemistry regions, we have sticking tendency and fine grains, cast grains. So for carbon equivalent less than 0.6, or for say 430, as I have explained for the stainless steel, we have soft solid shell of delta. Since we have delta ferrite solidification, and even after solidification also we have delta for a certain temperature, we know that delta has relatively less high temperature strength compared to austenite, so it is soft. Now when carbon equivalent is more than 0.2, this particular region, or Si 310, one popular stainless steel grade, we have thin solid shell of gamma. We have gamma is austenite, but the shell is very thin because of high incidence of microsegregation in austenitic solidification. So either for very low carbon or low nickel equivalent, chromium equivalent, we have a soft shell, or for high carbon equivalent or 310, we have a thin shell. So in either case, there will be sticking tendency and fine grains. Now I have mentioned what are the depression grades, which chemistry is prone to depression. So depression grades, and I have also mentioned depression grade means there is a formation of air gap on the surface of the solid shell, so the heat transfer comes down, so the grains, cast dendrites become more coarse. So what are the chemistry ranges? Where the carbon equivalent is around 0.1 for low alloy steels or plain carbon steels, or for stainless steel 304. So these chemistries are prone to depression and coarse grains. Why this is happening? Because the so-called peritectic grades, they start off, that means near the start of this peritectic reaction, delta plus liquid equal to austenite. They are called peritectic grades, but their chemistry is near the beginning of this peritectic chemistry range, around 0.1 or around 0.55 nickel equivalent by chromium equivalent. So they are the start of the peritectic chemistry, yeah. So what is happening here? Along with that, this transformation is delta to gamma. I have mentioned this is around the most brittle temperature region area, solid fraction 0.9 to 1. So additional shrinkage strain in brittle range. So this shrinkage from this transformation is adding to normal shrinkage in this brittle range between LIT, liquid impenetrable temperature, and actual solidus. LIT corresponds to solid fraction of 0.9, actual solidus corresponds to solid fraction of 1. So here we have thick and strong solid shell of austenite. At the end of the solidification, it is already austenite. So we have thick, because microsegregation is less, because initial solidification was through delta. So relatively thick solid shell, mushy zone is thin, and strong solid shell because it is austenite. So there are two broad categories of solidification characteristics and cast structure depending on the chemistry of the particular alloy. This we have to keep in mind. So the same thing I am trying to explain here schematically through the austenitic grain structure in solid shell. After solidification, beyond certain temperature, that means when we are cooling to lower temperature, finally all grades will become austenite irrespective of the chemistry, but certification mode, somewhere it is delta, somewhere it is delta plus gamma, somewhere it is only gamma austenite. So, certain chemistry range, as I have told you, will give you depression tendency, certain chemistry will give you sticking tendency or bulging tendency below the mold and sticking tendency inside the mold. So, when we have a sticking tendency, what do you have? We have fine grains. Solidifying is either through liquid plus delta or through liquid plus gamma. That means either very low carbon equivalent or very high carbon equivalent, either ferritic 430 or austenitic 310. So, these are the chemistries where you have this type of structure because of sticking characteristics. And in the peritectic grades, so called peritectic grades, where we have carbon equivalent of say 0.1 or AI is Si304 stainless steel. So, what is happening here? Initially liquid to delta and then it goes to delta liquid plus delta to gamma. That means gamma transformation is taking place towards the end of the solidification. So, this creates depression tendency. Depression means there will be an air gap between the mold and the solid shell. So, the solid shell will become thin because it is hot spot formation, this is a hot spot formation. So, heat transfer is getting affected, getting lower. So, we have coarse grains, though it is relatively magnified, you do not have so much of coarse grain. This has been done just to distinguish between the two characteristics, but nevertheless I will show it to you what are the grain sizes, cast grain sizes, what you get during casting of different carbon chemistries. But what is important here to see that for carbon equivalent very low, less than 0.5 or high more than say 0.25 or 0.3, you have relatively fine grain cast structure. Similar is the case for ferritic 430 or totally austenitic 310 stainless steel. But for the so called peritectic grades, that means chemistry near the start of the peritectic chemistry, that means around 0.1 or around 0.55 nickel equivalent by chromium equivalent for stainless steels, you have depressions. Because of that there is a gap formation, there is a, we call it hot spot formation. Because of that heat transfer is affected, becomes low, and we have coarse grain structure. So, cast grain is finer for a higher rate of solidification. If you have higher rate of solidification, cast grain will be finer. So, this is dictated by two things. One is the heat transfer in the mold, that means grades with sticking tendency you have finer grains, and finer grain is largely influenced by delta gamma contents during and after solidification, because if you have delta during casting and also at temperature lower than the casting, that means for very low carbon equivalent or say 430, where the delta to gamma transformation is taking place at quite lower temperature even after solidification. So, delta is present for quite some time, for quite a big temperature region. So, there is a possibility of grain coarsening of delta. So, there we have to be a bit careful. So, in such cases the earlier will be the onset of austenite, finer will be the delta grains. So, here the grains are coarser because of heat transfer considerations, because of solidification characteristics. Here delta to gamma in the solids transformation is important. If you can start that delta to gamma transformation at higher temperature just after solidification, you do not allow the delta grains to remain at high temperature for some time, quite some time, then you have relatively finer austenite grain size. Otherwise, relatively finer ferrite and austenite grain size. Otherwise, if you have large austenite grains, then you have some difficulty. Yeah, as I was telling you, we can measure the austenite grain size in the cast still. Now, how it is done? Say we can simulate continuous casting in a machine we call a glibble, is a simulator. So, what we can do is we can take a solid sample, say from from the different region of a cast product having different chemistry, and then we can heat it till it goes to the liquid region, and then we can simulate the continuous casting by cooling it at a rate which is equivalent to the continuous casting rate, cooling rate. So, in the glibble simulator we can use situation, cooling condition similar to continuous casting, and then we can see what are the phases present. We can interrupt the cooling at different temperatures and see what are the phases present, it is possible, or we can cool it to the room temperature at any rate what we want, and we see what was present at any particular temperature. So, likewise what we have done, we have tried to see for different carbon concentration, carbon chemistry, what was the austenite grain size in the cast steel after we have simulated in the glibble. So, we have found that 0.1% carbon, as I had told you, this is so called peritectic chemistry, we have relatively larger grain size, is around say 0.9 millimeter, is quite big. And when we come to say 0.3% carbon, you see it is relatively less, 0.4, so it is more than double. So, 0.1% carbon, as I was showing it here, peritectic grains means around 0.1% carbon, the cast grain size are relatively larger compared to the cast grains of austenite. So, you can see here actual measurements done during solidification, which has been simulated in a glibble simulator, glibble machine. So, the austenite grain size is quite large, around 0.9 is quite large. This of course cast grain size, and then for around 0.3% carbon it is decreasing as you are increasing the carbon. As I have told you, when you are going to say 0.3% carbon means you are coming to this type of situation where sticking tendency is quite high, and 0.1% carbon is a depression tendency. Depression means there is a gap formation on the surface, the hot spot formation on the surface, heat transfer is low because of this, and we have relatively coarse grains, cast grains of austenite. For sticking tendency, if you have very low or very high carbon, say 0.3% carbon, is a sticking characteristics. Sticking means there is no air gap formation between mold and the, relatively much less between the mold and the what is that called, solid shell. Here you see the gap formation is quite large, here gap formation is minimum, quite low. So, this possibility of grain coarsening is quite less here for sticker grades, but for depression type of grades you have possibility of grain coarsening. So, you can actually see what are the austenite grain size when you simulate under glibble. So, around 0.1% carbon is quite large, 0.3% carbon it is quite relatively less, so around 0.4 millimeter, and here it is about 0.9 millimeter. It's quite large size. So, we have tried to explain, depending on the type of solidification, there are two broad categories. One is sticker grades, that means which will have sticking tendency during solidification, and the grains will be finer, as I have explained. So, two chemistry ranges, you have such tendency, either the carbon equivalent is low, less than 0.6, or carbon equivalent is high, more than 0.2, 0.25, 0.3. So, or even ASI 430 is equivalent to very low carbon, or 310 which is equivalent to very high carbon equivalent, more than 0.5. So, this here you have thin, this for high carbon equivalent at 310 because of austenitic, totally austenitic solidification, you have thin solid shell of gamma. Because it is thin, it cannot withstand ferrostatic pressure, so there is sticking tendency. And for low carbon equivalent and low nickel equivalent by chromium equivalent, that means 430, you have soft solid shell because it is delta. So, that also cannot resist ferrostatic pressure strain, so it is sticking tendency. But when the carbon equivalent is around 0.1 or AISI 304 having nickel equivalent by chromium equivalent around 0.55, slightly more than 0.55, you have depression, so you have coarse grains, relatively coarse grains. The same thing has been explained pictorially. This for stainless steels, around 0.55 you have relatively high contraction strain, so you have depression. The bulging strain is relatively less, and for very low nickel equivalent by chromium equivalent, where the reverse is true, you have bulging, sticking, and for high nickel equivalent chromium equivalent, that is ASI 310 type of grade, we have again bulging. Similar effect for carbon grades, you see around 0.1 the strain, contraction strain is relatively high, so you have depression tendency, contraction or depression tendency, and for very low carbon or very high carbon you have sticking and bulging tendency. So, what is important is, again I am repeating, depending on the chemistry we have two broad transformation or the solidification behavior, either sticking or depression. And as I have told you, depending on this inherent characteristic, we can decide what should be the casting parameters. Because if it is a sticking grade, we have to take care of the sticking as much as possible, though it is an intrinsic characteristic. By continuous casting process, we have to take care of this problem, of this issue. So, if it is if the characteristic is other type, it is a sticking type, then we have to take care of it by controlling the friction. If you have sticking means what? Let us try to see what is going to happen if you have sticking. Yeah, if you have a sticking tendency, that means this solid shell is going to try to touch the mold surface. That means though in between you have a thin shell of thin layer of what is that called, powder, which is molten, that means slag, mold slag. So, the mold slag characteristic is to be such that this friction between the mold and the solid shell is relatively less, because sticking tendency means there will be more friction, the friction will be relatively high. So, the characteristic of the mold slag has to be such that this high friction can be taken care of. Here in peritectic grades, friction is not an issue, here the issue is gap formation. So, gap formation means the heat transfer is coming down. So, the powder characteristic and the slag characteristic will be such that this heat transfer has to be taken care of. So, it is the because of sticking, the friction has to be taken care of in mold, and here because of the depression tendency, this heat transfer has to be taken care of in the mold. So, as I have told you, depending on the type of solidification characteristic, we must use different mold powder having different characteristic. because here we have to take care of the friction. Friction is relatively high, we should not allow too much of friction, otherwise there will be sticker breakout. Here it is just the reverse, there is no sticking, there is air gap formation. So, heat transfer is getting affected, that means too much of depression. So, we have to control the depression, we have to see that the uniformity of heat transfer is there throughout the periphery of the mold, that is what is important here. Here what happens is at certain locations heat transfer gets affected. So, our mold powder should be such that it gives a mold slag which can control this heat transfer uniformly. So, here the heat transfer control is the main issue for peritectic grades where you have a lot of depressions. Our purpose is to control the depression, so through controlling the heat transfer. But for sticker grades it will try to stick more towards the mold, friction between mold and the solid shell is the issue. So, we have to reduce the friction between mold and solid shell. So, the powder has to be such that the mold slag should have such characteristics that it can resist the friction, it can lower the friction between the mold and the solid shell. So, here friction is the issue, we have to take care of that. Here heat transfer is the issue which we have to take care of by using proper mold slag. So, as I was telling you, depending on the characteristic of the alloy, we have to use different casting parameters, we have to use different casting powder. Casting powder is one, then I have told you about the mold oscillation. Mold oscillation also should be different, because what is the purpose of mold oscillation? Purpose of mold oscillation is to avoid sticking, to give lubrication. So, since the sticking tendency is high here, we should have mold oscillation of certain characteristics where the cycle of the frequency of the oscillation should be low and the amplitude should be high. Here for peritectic grades which have depression tendency, it is just the reverse. Here the surface, as I have told you, the oscillation depth is relatively more in peritectic grades. So, our purpose is to control depression and oscillation, depth of oscillation marks. So, here what we have to do? We have to use high frequency of oscillation with low amplitude of mold oscillation. So, the frequency is more here, oscillation is less here, frequency is less here, oscillation is more here. So, the powder is different, oscillation characteristics are different. So, we have to keep in mind, depending on the characteristic, solidification characteristic or type of behavior, solidification behavior, whether it is sticking type or depression type, we can design the casting parameters accordingly to get better surface quality, better internal quality of cast structure. Similarly, as I have told you, for this type of grades, normally you have to use relatively more of secondary cooling, intensity of secondary cooling. For such type of grades, we do not want high rate of transfer, heat transfer, not only in mold, even below the mold. So, the secondary cooling also is relatively less. So, depending on the grades, we have to design the parameters, casting parameters accordingly. Thank you very much.